research on the quantum interference patterns in single photon double slit experiment. And I'm Victoria Zhang, and my mentor was Kanupriya Sina. And so basically, light in the everyday world is seen as a wave, but in reality, when you look at it on a smaller scale, such as in like the quantum mechanics, light is actually small particles known as photons. And so basically, in my paper, I discussed the photoelectric effect and the double slit experiment. And we further explored the double slit experiment and how various features of light, such as the intensity or the wavelength, can affect the interference pattern. So basically, the photoelectric effect is when you shine light, like low light, on a metal surface, you will find that particles of light or photons get ejected. And basically, in the 20th century, physics believe that when you shine the light, the intensity of the light affected the kinetic energy of the photons that would be ejected, while the frequency of the light would affect how many photons were ejected. But in reality, when they actually conducted the experiment, they found out that it was the frequency of the light that affected the kinetic energy, while the intensity or brightness of the light affected the rate of emission. And so basically, this led to Einstein to create a new model for light, and he basically suggested that light was actually particles of photon. And so basically, here in this image, you can see that like light with low frequency or red light could not eject the photons, while green light with a little higher frequency ejected low energy photons, while this blue light ejected higher energy photons. And so then the double slit experiment shows like the wave and particle duality behavior of light. And basically in the double slit experiment, the light shines on a screen that has two parallel slits, which are very close together. And this creates an interference pattern that is shown on a screen behind the slits. And basically, Thomas Young, who originally did this experiment, he only did this to prove the wave-like behavior of light. And so basically, in the experiment, when the light is shown on the two slits, the light waves will radiate outwards, and they will create this interference pattern of light and dark stripes. And basically, when the peaks of the light to waves from the slits, the peaks will strengthen each other to create this bright light, while the peaks and the troughs, they will cancel out and create this dark light. And when this experiment was done with particles of light, they originally thought that it would create two strips of light because of the two slits, and they didn't expect anything else because they were particles. But when done, it actually resulted in the interference patterns seen with the waves. And this basically showed that light could behave as not only a wave, but also a particle. And so basically in my paper, I studied how different factors of the light in the double slit experiment could affect the interference pattern. And basically it involved like geometry and trigonometry. And I started by using this model by labeling the slit separation, which is D, and just setting like variables for these quantities, and also the distance between the slit and the screen, and also the center line. And we wanted to find the relation between this angle and the interference at y1. So basically, just by creating these lines, we created 3 angles, which would help solve that. And using the tangent, and then we found the tangent of these angles using the variables that we set. And then this bottom line was then split into 2 segments, one which is equal to this smaller segment because it travels a smaller distance, while this and so it basically created an isosceles triangle, and this smaller segment created another triangle with the base of this isosceles and the slit separation. And when you rotate this smaller triangle clockwise or counterclockwise, it actually lines up with this blue line and the center line, meaning that this angle right here is equal to this angle. And through this, you can find the center of the bright fringes and the dark fringes as seen in these 2 equations. And basically, you can see that an M would be like the location of the fringes. And so the bright fringes, they happen at when the wavelength is full, so it's just M. And then the dark fringes, they happen at odd wavelength, so you would add half. And then the result was also measured in distances from the center line. So basically this incorporated the tangent from the equations above. And this was just to find the bright fringes and the dark points using the distance L. And also, since the previous equations are defined like the totally bright and the completely dark points, this method was used to find the places in between, and this involved the intensity of the light. And so basically, I is just the intensity and IO is like the combined wave intensity. And basically you get this equation. And so ultimately from the equation 8 and 9, which are these 2, you can see that the location with the totally dark and bright fringes are dependent on the wavelength and the incoming light and the distance between the 2 slits. So basically, if you increase the wavelength, then the spacing between the fringes would also decrease, while if you decrease it, then the spacing would be smaller. And also, if you increase D, the slit separation of the fringes decrease and vice versa. And for equation 10, you can see that with distance L, if you increase the spacing from the screen to the slits, then the spacing between the pattern would increase. And lastly, if you increase the intensity of the light, then you can see that the dark and light fringes would increase. And so basically, by understanding the double slit experiment and the photoelectric effect, it fundamentally changes how we perceive the nature of light, and that light is not a wave or a particle, but rather something in between, since it has characteristics of both. And basically, this knowledge of quantum light paves the way for new kinds of information processing technologies, such as GPS computers, medical imaging, and global communications networks. And currently, the quantum nature of light has applications in developing new kinds of computers called quantum computers, which operate using qubits. And these computers have the potential to process large amounts of data in a faster manner compared to classical computers. And that's my research. Thank you.